Assalamu alaikum. Welcome to lecture 21 of data mining. So we were discussing clustering algorithms in the past 2-3 lectures. So we will continue with that discussion today. We had started talking about density-based clusters and density-based clustering algorithms. And we will discuss density-based clustering algorithm at the start. And then we will discuss graph-based clusters and graph-based clustering algorithms later on today. So I think that's the two main points that we'll be discussing today. Subsequently, I think the following lectures will be discussing evaluating clusters. I think that will take 1 or 2 lectures. So far, while we were discussing clustering, we did not focus on evaluation, even though evaluation is an important aspect in all of data mining. So we will collect some evaluation techniques at the end and discuss them maybe in the next lecture, starting in the next lecture. So that's the agenda. So are there any questions? Any questions? All right. So, okay, so let's start with density-based clusters. So density-based clusters are defined by density. So a cluster which is density-based essentially presents regions that have density greater than some given threshold. And density-based clustering algorithms basically then process data such that they are able to find clusters that are defined by density. So generally, density-based clustering and density-based clusters are local criterion in the sense that we're only considering a neighborhood of a certain point or some points. We don't look at all the data sets at once or while deciding a cluster at a given region. So as such, it's considered to be a local criterion as opposed to, for example, the k-means algorithm, which uses a global criterion. So one of the key advantages of density-based clusters is that it can find clusters of arbitrary shapes. So in the k-means or k-medoids approach, we were only able to find clusters that were more or less spherical in n-dimensional space, meaning that they were convex or globular in nature. While in density-based cluster, you might find clusters that are concave or non-globular. You might have edges or paths and so on. So that's possible. Any region in space that is dense would be found through density-based clustering algorithms. Density-based clustering algorithms are also good at handling noise. And one of the reasons for this is that we are always considering points in relation to its neighbors. And that's how essentially we define outliers. So while we are doing density-based clustering, we are also in a way filtering out or finding or identifying outliers as well. And we will see this, and we will discuss outlier analysis in detail as well after finishing clustering. And we will see that almost all of the algorithms for outlier analysis are clustering based. So you typically need one scan over the data set, but of course that one scan would require n square or n log n operations. So, and density-based clustering algorithms have some parameters, and many of these density-based algorithms are sensitive to the selection of these parameters. Of course, these parameters do not include the number of clusters. The number of clusters is automatically found by the algorithm. The parameters are the parameters for defining the density. As we will see, is EPS and min points. EPS is a radius parameter, and minimum points is the number of points in that radius. So there are various algorithms in this category. We will only discuss one in some detail. There are others with variations. So we will basically be discussing the DBSCAN algorithm. So to understand density-based clustering, you need to understand some concepts. We had started talking about this last time as well. So there are two parameters in DBSCAN, for example. So one is EPS or epsilon, which is the size or the radius of the region around a point, the maximum radius of the region around a point. In other words, this EPS defines the neighborhood around a point. And then the other parameter is min points, which is a minimum number of points in this region to make that region dense. So both these parameters control the density. For example, if you reduce EPS and you keep min points fixed, then of course, basically you will have to have more points, or you have to have so there's less likely that that smaller region would be dense because min point is fixed. If you increase EPS and min points is of course fixed, then of course there's greater likelihood that a region becomes dense. So you can control the density through this these two parameters. So the neighborhood around a point Q is defined by n. N is for neighborhood, not number. So n EPS, of course, is the parameter of a point Q, is basically the set of points for which the distance from P to Q is less than or equal to EPS. Okay. So this is the definition of the neighborhood around a point Q. And then based on this, there are a couple of definitions. We discussed three definitions last time: core points, border points, and outliers. There are a couple of others as well: directly density reachable and density reachable, and of course density connected. So let's discuss this. Maybe I can go back to my slides. So we talked about core point, we talked about border point or object, and then of course outlier. So core point, for example, Q is a core point if ठीक है, n EPS Q is greater than min points. Okay. So what does this mean? N Q is basically the neighborhood around Q, and this neighborhood is defined by EPS. If the number of points in this neighborhood is greater than minimum points, which is the other parameter, then Q is a core point. So in other words, Q lies at the center of a dense region. Okay. So that's a core point. What about border point? So Q is a border point if it lies in some n EPS P, of course we're talking about Q, it lies in a dense region defined by P, and Q is not a core point. Okay, so do you understand this? So in other words, Q is a point in the neighborhood of P, where P is a core point, but Q itself is not a core point. By the way, if Q itself was a core point, that would be a core point. It would not be a border point. So Q is not a core point, but it lies in a region defined by a core point. Okay. And then, of course, outlier. So if Q is an outlier if it is neither a core or border point. Okay. So anything that does not lie in a dense region is an outlier. And of course, as I said, density is defined by those two parameters, EPS and min points. So, so I hope this is clear. Based on this, we have a couple of other definitions. One is directly density reachable, or DDR. So the first three definitions were for points. Now we are talking about 2 points, not 1 point. Okay. So Q is directly density reachable from P, okay, 2 points, if so you can define this in different ways. If Q lies in n EPS P, okay, and P is a core point. Okay. In other words, Q is a border point of P. Q is a border point that lies in the region P of P, where P, of course, is a core point. So we say that Q is directly density reachable from P. So P is a core point and Q lies in its region. Is that clear? So let's see if I can, although I think figures wouldn't be too helpful. So basically, if we talk about P as a core point, let's say I mentioned core point as a plus, and this is the region around it, then Q lies here inside the core point, inside the region defined by the core point around P. So if Q is not a core point, then of course it is a border point. Okay? And we say that Q is directly density reachable from P. So that's one definition. The other definition is a slightly relaxed version of this. Which is simply density reachable, not directly density reachable, which is, you can say, DR. So Q is density reachable from P if there exists a sequence of intermediate points P1, P2, such that that each preceding point is, for example, such that so we have Q and P, so such that so for example P1 is directly density reachable from Q, and P2 is directly density reachable from P1, and so on. And finally, P is directly density reachable from P whatever n. So you have a sequence of core points that lead to this point P. Sorry, Q देख रहे थे ना, Q. ठीक है, this is Q. So the final point that we're talking about is Q. So if I want to draw this, so you can think of, we are talking about, of course, we are talking about Q. This is Q, and we are talking about some P here. So we say that Q is density reachable from P. So how would that be reachable? So basically, let me draw this again. So basically, we are talking about Q being directly density. Let's say Q इधर है और P इधर है, ठीक है ना? तो इसका मतलब है कि बीच में मेरे पास P1 आएगा, P2 आएगा, P3 आएगा, and of course Pn. All of these P1 to Pn are core points, including P is a core point, such that ये P है, this is a core point, उसी के अंदर ये P1 जो है ये उसके region के अंदर है, but itself P1 is a core point. उसका एक अपना core point बनेगा, उसका अपना एक core point बनेगा, उसका अपना एक core point बनेगा, उसका बने until we reach our Q. So Q, of course, is not necessarily a core point, but there is a path of core point that leads to Q. So obviously this, as you can see, this leads to the notion of cluster. So ये आपके पास एक core point के circle है, ये core का 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 है, ये core का, until you reach this point Q. So ये जो सारे जो circles को आप join कर दें, this is the cluster that is formed. So each of these circle represents a dense region and they overlap. And if you combine that overlap, then you get a cluster. So in essence, a cluster is a maximally connected region of points, of density connected points. By the way, density connected is another definition. Density connected essentially means that two points are density connected if there is some P, which is a core point from which they are density reachable. And all density connected points that are part of some core point would form a cluster. So basically density connected. So P and Q are density connected if there exists some point O from which P and Q are density connected, meaning that P and Q are in the same dense region that contains O, and O of course would be a core point because it's a point from which density reachable. Okay. So P and Q are densely connected if they are densely reachable from a core point O. And finally, a cluster is a maximally, or maximal, you can say, maximal, meaning that the largest set, maximal number of densely connected points. So essentially, these definitions are meant to precisely define a cluster in density-based clustering. Okay? EPS and min points are the two important parameters. Based on those parameters, we are kind of grouping points to form clusters. So that grouping is based on the notion of density connectivity, and density connectivity is based on the notion of density reachable. And of course, density reachable is a relaxed version of directly density reachable. Directly density reachable, of course, is one region. So density reachable could be multiple regions. And within that, of course, you have the notion of core points, border points, and outliers. Okay, any questions? So now, what is the algorithm for DBSCAN? So this was essentially a definition. The algorithm itself is quite easy. And of course, we are talking about clustering. So we have n objects, obviously in the data set, K is not an input parameter. We only need EPS and main PTS as input parameters. So given these as input parameters, we essentially randomly select a point P. Okay. And of course, we have selected a point P, we have to find its neighbors, and based on its neighbors, we define its region. In other words, we find all densely connected points of P. Okay. So if P is a core point, of course, it would have a region of its own. It will have some border points. Okay. And if it within its region, it has some other points that are also core point, then this region would continue. So, and of course, all that continued region would form the density connectivity. Okay. And that's of course a cluster. Okay. So you have to go to each point, random point P लिया, उसके पे neighbors में points देखा, फिर देखा वो भी core हैं कि नहीं है, and then you continue in that fashion. So in other words, you are basically saying determine whether P is a core point, border point, or outlier. I think किसी का mic unmuted है. Okay, I think that's fine. ठीक है. So once you're done with P, you go to the next P, and you continue in this fashion until you have processed all points. So essentially what happens is the loop is over all the n objects. But whenever you select one object, एक P आपने select किया, उसके आपने इर्द-गिर्द neighborhood देखनी है. In the worst case, neighborhood में सारे other points भी होंगे. ठीक है ना? Because आपको किस तरह पता चलेगा कौन सा पॉइंट नजदीक है कौन सा दूर है, सारे पॉइंट देखने पड़ेंगे फिर पता चलेगा कौन सा नजदीक है कौन सा दूर है. सो इन द वर्स्ट केस ऑफ कोर्स इसकी कॉम्प्लेक्सिटी n स्क्वायर है, which is like the complexity of the k-medoids or, for example, the hierarchical clustering approach. But if you are able to use a distance-based indexing approach, then this might be reduced to n log n. If a based indexing structure is used. ठीक है जी, हमने बात हायरार्किकल क्लस्टरिंग के लिए भी की थी. ठीक है, so the same thing applies here. If you don't use this, then in the worst case, of course, you will be doing n squared operations to do the clustering. ठीक है, take one point, find its neighbors. Go to the next point, find its neighbors. So obviously, n square operations. So this is essentially what DBSCAN is. There are many other variations of this, and many of those variations actually worry about how these parameters are selected and updated. So we talked about two parameters, EPS and min points. So if, for example, for a fixed EPS or for a fixed number of min points, you increase EPS, you are now considering less dense regions. If you decrease EPS, you're considering more dense region, and vice versa. If you fix EPS and you increase minimum number of points, you are now more interested in denser regions. And if you decrease EPS for a fixed, decrease minimum points for a fixed EPS, then of course you're considering less dense regions. So these two parameters do control the density and the eventual clusters that are formed. And it's quite sensitive actually. So oftentimes in practice, if you're not using some of the more advanced techniques, you will have to try with various combinations of these parameters to find the best clusters in your data set. Of course, the variations that work on this in a systematic way, one variation is called optics. आपके book में है, but हम cover नहीं करेंगे in detail. Optics is a technique. Of course, many of these techniques are very fancy name. So ये काफी trend था data mining में in the early 2000. but ये अब खैर खत्म हो गया. So DBSCAN or optics or a priori or FP growth, all of these are algorithms from the early 2000s, maybe late 1990s. Okay, so I think that's essentially it for density-based clustering. The key benefit of density-based clustering is K is of course not required, and then secondly, it can find arbitrary shaped clusters. Shaped clusters can be found. So the clusters may not be always spherical in shape. And of course, the clusters could be of different sizes as well, according to the density in the data. And thirdly, of course, noise can be handled intrinsically in the algorithm. Outliers can be handled intrinsically. Remember, we said that if a point was neither a core point or a border point, it was an outlier. So outliers are identified as part of the clustering algorithm. Okay, so any questions? So density-based clusters in some ways is a generalization of your prototype-based cluster, especially the single point prototype-based cluster. So by setting the parameters min points and EPS in a certain way, you can get the same clustering that you get through, for example, k-means and through DBSCAN. So in other words, you can say that k-means is a specialized version of DBSCAN. I mean, in terms of the clusters that are formed, not the algorithm, of course, algorithm is different. In terms of the clusters that are formed, the clusters that are formed through DBSCAN may be identical to those formed by k-means by selecting some appropriate parameters, EPS and min points. Okay. So this is something else that you need to be aware of. But in general, for any practical problem, it is kind of very hard to find the EPS and min points that would give us the same clusterings as a particular k-mean algorithm applied to the same data set. But theoretically, it is possible. So now let's move on to graph-based clusters and, of course, clustering algorithms. Okay. So first of all, just like we did for density-based clusters, so graph-based clusters are defined by some concept from graph theory. So graph-based clusters are defined by, you can say, connected portions of graph. So density-based clusters were defined by dense regions. Graph-based clusters are defined by connected regions or compact regions within a graph. All right. So of course, we said that you need to have a graph. So we need to have some idea what a graph is and how we can represent a data set as a graph. So in general, a graph is a set of two things, vertices and edges. Okay? So V is vertices and E is edges. So this is what a graph is. So in our case, vertices are points or objects in data set. Okay? So of course, in which case, so would be to n. Okay? So the size of the vertices set would be equal to n, which is the number of data points. So E is the between objects, and this connectivity captures similarity between objects. Okay? Again, we are trying to relate our problem to the problem of we are kind of mapping our data set to a graph, and of course capturing information that is relevant for clustering. So nodes or vertices are objects, and the edges between those vertices represent similarity or dissimilarity. Okay? Of course, graphs can be directed and undirected, as you know. So directed and undirected. in general. In the context of clustering, we are primarily interested in undirected graphs, but the interesting thing is that even if you have a directed graph, and if your problem does lead to a directed graph, you can still do clustering, graph-based clustering, which is an interesting thing. And we'll discuss this shortly. So let's say you have created a data set, and you have a data set and you want to create a graph from it. So what can you do? So let's say you have it. So for example, let me start first with some problems naturally lead to a graph. So for example, if you talk about the friend network on, let's say, Facebook, this can be naturally mapped into a graph. So each node or vertex is a person, and the connectivity represents friends. Okay. Of course, in this case, the connectivity of the edge between two nodes is either exists or does not exist. If it exists, it means that they are similar, or in other words, you have a similarity of 1. If there is no edge between two friends, then there is no similarity. Or in other words, the similarity is 0. Okay. And so in this case, a graph naturally arises from our data set. And then you can do clustering. If you do clustering on such a data set, what would you find? You would find communities of individuals, which is groups of individuals that are friends among themselves, and of course they will be friends among themselves because they share common, you can say, interests, and those groups of common interests essentially are communities. Okay. So in this case, of course, the edge is undirected. So if X is a friend of Y, Y is also a friend of X. But sometimes you might get a directed graph. So for example, let's say you have the hyperlink structure of web. Okay. So in this case, so let's say you have a page A. A has a link that points to a page B. And perhaps B does not have a link back to A. So in this case, you will get A. So B might have a link maybe to C, and B might have a link maybe to D, but it does not have a link back to A. So again, now we have a graph. Each node represents a page on the web, and the edge, which is now directed, represents whether from that page there is a link to the other page. So here again, of course, a link represents a connectivity. No link means no connectivity. It means that, in other words, a link represents similarity. No links represents dissimilarity. So binary kind of relationship. Okay. And of course, you can get natural graphs from many data sets. So I just gave you 2 examples. One example was, of course, for the web pages. The other was from Facebook, let's say. You can also have, so for example, the issue of Facebook, or even let's say, yeah, Facebook is fine. So in that case, let's say you have A and let's say B are friends. You have a link between them. But maybe the strength of the link can also be indicated. Rather, instead of just being binary, friend or not friend, maybe you can weight this link with maybe the number of messages that are shared among these 2 people. So edges can be weighted as well, okay, rather than just being binary. And this can also then be captured in the clustering algorithm using the graph. So one category is your data set naturally maps into graphs. So secondly, let's say if maybe it's not very intuitive to map your data set into graphs, but you can still create a graph for almost all clustering problems. So let's say you have a data set and you have a data set X, of course, D, which is of course your Xi, I is equal to 1 to N. Okay. So the question is, how do you construct a graph from this? Okay. In the first case, in the first category of examples, graph was quite of natural. So in this case, of course, if you have a similarity function that can define the similarity or dissimilarity between 2 points in the data set, you naturally have a matrix, similarity matrix. Okay? So let's say I call this similarity matrix S. So Sij is basically the similarity between Xi and Xj. Okay? And this is a value from 0 and 1, let's say. So 1 means full similarity, 0 means okay, in a value between 0 and 1. So let's say if you have this, and for most clustering problems or all clustering problems, you should have a way of quantifying the similarity between 2 points. So that's a requirement for clustering. So from this matrix, you can construct a graph. So how? So simply take the similarity value as the weighted edge between those 2 points. Okay. So let's say if we have a point x1 and a point x2, the similarity between x1 and x2 is, let's say, 0.1, then we will connect x1 and x2 with an edge weighed as 0.1. Okay. So you get a graph from this. Very easy, right? But one issue with this graph, and especially for graph processing and for graph-based clustering algorithms, is that this graph would be highly connected. You would find very few objects in your data set in which similarity is equal to 0. Almost no objects in the data set with similarity equal to 0. So you will have some similarity, 0.001, for example. Okay. So in which case, you will have almost a fully connected graph. And generally, the complexity of graph processing algorithms would explode with the number of connections between the nodes in the graph. So we will typically like our graphs to be sparsely connected or less than fully connectivity. So how do we get then sparser graphs from similarity matrices? So there are actually two approaches to get basically the first approach is, of course, threshold the similarity. Okay. So, for example, if So if similarity is less than, let's say, some small value epsilon, then do not connect the objects or nodes corresponding to those objects. Okay. So for this case, of course, you will have to select this similarity value or decide the similarity value a priori. And based on that, some edges would be dropped and the remaining edges would remain in the graph. So that's one approach, which is kind of a global approach because the same similarity value is applied throughout your data set. Okay. So the other approach that is commonly used is the approach which is called the K nearest neighbor approach. By the way, this K nearest neighbor is not clustering, it's not classification as we discussed earlier on. So this is just the K nearest neighbor and you connect them. So instead of fixing the threshold for similarity, we fix the number of the most similar objects that we want to connect for each object. So K is the number of neighbors to connect. Okay. So for example, let's say you have let's say 10 nodes, for example, x1 to x10. Okay. And let's say all of them have some similarities. All of them, if you don't threshold them, they will be connected, fully connected. X1 will be connected to every other node. But now instead of fully connecting them, we select the, let's say k is equal to 3, for example. The k most similar objects to x1 and connect them to x1. Okay. So k is now a parameter here, just like threshold was a parameter in the previous case, similarity threshold, epsilon. In this case, k is a parameter. So now for each node in your graph, the degree of the node would be 3. Degree, by the way, is the number of edges that either are incident or actually we're talking about mostly undirected graph, that degree of edges that basically connect or point to a particular node or vertex in the graph. So when k is 3, then all edges would have a degree of 3. And then if you have 10 objects in a data set, so there will be 7 links that would be dropped per node. So both of these approaches can be used to create sparser graphs from similarity matrices. Generally, the k nearest neighbor approach is preferred. And one of the reasons for that is that this approach is local in the sense that if your data set have varying densities, then in a region which is less dense, the similarities might be large, but you still be capturing the 3 closest or most similar objects. In denser regions, you will have still the 3 nearest points being connected, and those points would have higher similarity. So points would be closer in some regions and further away in some regions. So for example, let's say ये एक dense region है, तो आपने हमेशा हर एक पॉइंट के 3 नियरेस्ट नेबर्स ढूंढने हैं. So इसमें जो लाइंस हैं, of course I'm plotting this in scale. Lines represent now the distance between the points. So now the distance between the points is small, meaning that they are very similar. So let's say उसी डेटा सेट में एक और रीजन भी है जिसमें पॉइंट्स काफी दूर हैं. इसमें ऑफ कोर्स जो 3 नियरेस्ट नेबर आप ढूंढेंगे तो वो दूर दूर होंगे. So in other words, your graph basically, so your graph basically adjusts to the local density in the region. On the other hand, if you are fixed a fixed similarity, let's say आपने एक similarity fix कर ली होती, तो maybe ये जो sparse region था इधर वाला, all of them may not be connected. So ये निकल जाता आपकी clustering में से, connecting कोई नहीं होती, because similarity इसकी let's say 0.3 से कम है, तो ये सारे निकल जाते हैं. But in the case of k nearest neighbor, उनके 3 points फिर भी connect हो जाएंगे. Of course, k can be any number from 1 to some higher number, let's say usually 7 or 9 and so on. 1 भी कर सकते हैं आप. And this is a parameter that you can play around with in your clustering algorithm. Okay, any questions? Okay. So we have discussed how to get the graphs. Either they are natural from the data set, or we can use the similarity matrix to convert that into a graph. So now we have a graph. How do we do a clustering? We have obtained a graph now, G of the data set D. So now we'll like to do clustering using this representation of the data, the graphical representation of the data. So in this case, actually there are tons of algorithms here, and we won't be able to discuss almost many of them. So I'll just give you some ideas and discuss maybe 1 or 2 algorithms in somewhat more detail. One approach is you can probably use your graph theoretic approaches. So maybe you study this in some advanced algorithms course. So one idea is, for example, the idea of min cut. So we want to given a graph, we want to cut the graph into 2. And we want to cut it in such a way that the edges that are cut have the minimum weight. So here, of course, weight would be similarity. The minimum similarity means that those points are far away and they can thus be cut away. So there are techniques for finding min cuts in clustering. So for example, let's say आपके पास कोई graph structure आ रहा है, ये कोई connected graph है यूं करके, and then you have one long edge here है, फिर ये connected graph है यूं. So obviously min cut would be this one. This long edge basically means that the distance बहुत दूर है, similarity थोड़ा. ठीक है? So your graph clustering algorithm, min cut clustering algorithm, cut this into 2. So once you cut this into 2, you get 2 clusters. And then you can do it recursively on the 2 cluster itself. So min cut algorithm is chalta hai. Of course, this is the concept of the min cut algorithm. Algorithm itself we are not discussing. Okay. So generally, these approaches would be working in a hierarchical fashion. So you given a graph, you do a first cut that will split it into 2. Then you take each of those graphs again and then cut it into 2. You further get 2 more clusters and so on. So एक किस्म की hierarchy बन जाएगी. So that is one way of doing it. And also in general, from graph theory, you know that the idea of a clique. What is a clique? So if you have n points, let's say n points are, so let's say m points, some subset of the n points, if all of those m points are fully connected, so then that's a clique. Of course, here we are not considering the weights of the edges, but just looking at that, assuming that they have edges. So obviously a clique is a fully connected region. It means that this is potentially a cluster. So finding cliques might also be a technique for finding clusters. Okay. Okay. The next class of techniques, again, we are not probably going to discuss in detail, is called spectral clustering. So spectral clustering basically is, you can say, mathematical clustering. We basically have an adjacency matrix, or sometimes affinity. Essentially, affinity matrix is simply a similarity matrix, but in graph theory, we call it a affinity matrix. And adjacency matrix is a similarity matrix, binary similarity matrix. Either there is a connection or there is no connection. So for example, Aij would be 1 if xi and xj are connected. Which means that, of course, similarity xi, xj is equal to 1, maximum similarity. And of course, 0 otherwise, meaning that if the similarity is not 1, then they are not connected, and of course, the value would be 0 in the adjacency matrix. Affinity matrix, of course, is actual similarity. Okay. So the spectral clustering algorithms actually work on this matrix in a mathematical way, finding eigenvalues, eigenvectors, and those eigenvectors and values essentially then define your clusters. So as I said, I wouldn't go into the detail of this. I think you study this sometimes in some other course as well. मेरे ख्याल से ये big data analytics में भी study किया जाता है. So essentially, you basically do eigen system analysis of the matrix A. And from this, you are able to identify clusters. So these techniques are sometimes computationally expensive because eigenvalue analysis is generally computationally expensive, and our matrix A would be quite large. हम जब data mining की बात कर रहे होते हैं, कोई few hundred examples नहीं होते. We are talking about tens of thousands of examples, and performing eigenvalue analysis on tens of thousands, even millions of objects is not a trivial task. It's kind of quite complicated. So that's why in data science and data mining, usually spectral clustering is not a preferred technique. Although theoretically it's a good technique, but not used much in practice. So finally, there are a number of, you can say, less theoretically sound techniques or heuristic-based techniques that do pretty well for most data mining tasks, where you have lots of objects. And I'm going to discuss just one of them. We have 15 minutes, so let's discuss that. But this algorithm that I'm going to discuss, there are many variations of it with the same concept, and you can study that at your own time. So we are going to discuss one specific version, which is simple version, has a fancy name called Chinese whispers clustering. Okay. So Chinese whispers, of course, is the name drawn from a game, which essentially means that one person speaks to another person something, that person then communicates it to something else, the same idea to someone, and then someone, and so on. So again, this gives you the notion of connectivity. So वही graph based approach है. And the generalization of this is also used, and उसमें आपको उस नाम से भी आपको different नाम से भी और techniques मिल जाएंगे. For example, Markov clustering. So Markov clustering also talks about a chain. So Markov clustering is, you might find this in the literature as well. There is also message passing based clustering. So these are some of the names of the algorithms in this category, and most of these algorithms are similar. Message passing clustering, again, you pass some message from one node to another node, from another node to another node, until you get basically if that message comes back to you, and based on that you are able to do a clustering. So let's specifically look at this particular algorithm, Chinese whispers. Okay. Chinese whisper, by the way, is not in your textbook. इसका एक paper है छोटा सा, वो मैं share कर लूँगा later on. You can always find the paper on the web as well. Okay. So what is the idea? So you have the A, which is adjacency matrix. So this adjacency matrix can be binary, meaning the 0, 1. It can also be weighted, meaning that it's weighted with similarity. Okay? Meaning that A then becomes an affinity matrix. So this defines your graph, of course. Okay? And then we have another matrix D. This D is not the data set. This is a D that is used in this algorithm. By the way, so we have, let's take some numbers, n objects data set. So this matrix A would be of size what? This would be of size n by n, right? So you have a similarity defined for every pair of objects. By the way, this A matrix need not be symmetric. So if it is a directed graph, then the similarity between x1 and x2 may be different from the similarity from x2 to x1. Of course, it wouldn't be similarity as we defined it. It would be some other concept, but it can still work on directed graphs as well. Okay? So that's a good positive of graph-based algorithms. So we define another matrix. This is basically called the graph assignment matrix. Oh, sorry, not the graph assignment matrix. The cluster assignment matrix. Okay, and this is also n by n. Okay. So now let me now discuss the algorithm, and then you will understand the intuition. So what is the algorithm? So basically we start, okay, the clustering assignment matrix D, ij, so the intuition of this matrix D is that the n columns, of course, and they of course n rows, but let's say we focus on a column. ये एक column है इसका. Each of those columns represent the clusters. Each of the rows represent an object. So you can think of n clusters and n objects in the extreme case. Like in hierarchical clustering, you start with each object being its own cluster. But essentially what I want to mention is each column represents a cluster. So if you have a 1 there at some point, इसका मतलब है कि वो वाला ऑब्जेक्ट जिसका रो में 1 आ रहा है वो उस क्लस्टर में लाई करेगा. So this is the interpretation of this matrix. So if I want to draw this, so let's say ये आपका एक कॉलम है इस मैट्रिक्स का. If there is a 1 here, इसका मतलब है कि ये ऑब्जेक्ट ये वाला था, it belongs in this cluster. If there's another 1 here, तो मतलब ये दोनों ऑब्जेक्ट्स इस एक ही क्लस्टर में हैं, because they lie in the same column. And of course, this D matrix only has zeros and ones. It's a binary matrix. So at the start, we assume that each object it's its own cluster. Diagonals में हम 1 डाल लेते हैं, बाकी सारे 0 होते हैं. इसका मतलब है कि object 1 is in cluster 1, object 2 is in cluster 2, object 3 is in cluster 3, and so on. ठीक है? So this is the starting condition. So basically at start, you have ones in diagonal of D. ठीक है? And then we have a loop. And loop में आप दो चीजें करते हैं. Let's say I say D prime, this is a matrix D prime. I multiply this D and A. ठीक है? So what is D and A multiplication? A is the adjacency matrix or affinity matrix, or D is the assignment matrix. So based on the assignment matrix, and you multiply this affinity matrix, all those ones, if you do the, we could probably do this next time. जब ये मल्टीप्लिकेशन करेंगे तो जितने भी कनेक्टेड नोड्स हैं उनका सम हो जाएगा सिमिलैरिटी का, और वो उस पॉइंट पे आ जाएगा. So in other words, we are summing the similarity of objects to which a particular object is connected. ठीक है? And based on that sum, we can, so next step में basically D जो नया D जो बन रहा है हमारा, it's simply basically the max for each row in the matrix D prime, and then basically end loop or continue loop until there is no change. ठीक है? So जो final D आएगा आपका, so final D represents the final clustering. How? So you look at each column और उसमें देखें कि कौन से ones आ रहे हैं, तो इसमें मतलब उस cluster में वो points हैं. Maybe they at the end there might be some column that are all zeros. इसका मतलब है वो cluster नहीं है. In essence, at the end you may have less than n clusters. There might be some columns that are all 0. Some columns would have ones, so those ones represent the objects in that cluster, and so on. So again, in this algorithm, K is not an input. The number of clusters is not an input. The number of clusters is determined automatically from the data set. ठीक है, तो I think I will probably stop here. Next time मैं इसका पेपर भी शेयर कर दूंगा, और then we'll just look at a quick intuition behind this from a non-matrix perspective, and by then you should be able to understand कि ये क्यों ये हो रहा है, why we are selecting this and why this column represents a cluster. So with that, actually, we will be concluding our discussion on clustering algorithms. We will then move on to evaluation of clustering, and which will then probably start in the next lecture. Okay, any questions? Any questions? ठीक है, तो I think we should we end this session and we'll meet again inshallah on Tuesday. Tuesday को आपका 8th quiz भी हो जाएगा, and looks like we might have 9 quizzes, और 9 quizzes हो जाएंगे तो फिर probably हम 2 ड्रॉप कर देंगे.